Good afternoon, everybody. Thank you for tuning in to this webinar on Flexlines, a program to build infrastructure and design tools for flexible electronics in the Benelux. We have not all attendants tuned in, but I guess it's time to start. I'll start by explaining briefly the topics we are going to go through this afternoon. If there are any questions, there's a public chat available to you where you can post your questions, and either at the end of each speaker or at the end of the webinar, we will compile these questions and we will try to go into them. So first off, I will introduce the project and some of its key players. After that, Romano Hofman from IMEC will take over and introduce you to the one-stop shop concept, the easy access that we are creating for the design and realization of flexible electronics. After Romano, it's time for Auke Kronemeyer from TNO, who will explain the infrastructure that is being built to realize these flexible electronics products. And then at the end, Mohit Andekar from KU Leuven will explain us how you can design electronics systems in this new flexible, foldable paradigm. Flexlines is a regional collaboration between a number of players and receives support from Europe. Interreg Vlaanderen-Nederland is supporting this program, along with the province of Noord-Brabant, FLYO, the province of Oost-Vlaanderen, and Smart Hub Vlaams-Brabant. The objectives of the collaboration are threefold. First of all, to beef up the infrastructure in the region with regards to production and prototyping of flexible electronics. Within the project, we are rendering operational significant amount of square meters of production lines for flexible electronics. Secondly, in order to enable access, we are setting up a one-stop shop for easy access for innovative companies that want to engage in realizing flexible electronics products. And thirdly, within the project, we want to realize a number of demonstrators to show that what we have built is actually working and operational, and to demonstrate a number of showcases to entice companies that potentially might be interested in flexible electronics to actually make use of these opportunities. The actors in this collaboration are IMEC, CMST, the Center for Microsystems Technology from Ghent, Holst Center, the collaboration between IMEC and TNO, TNO itself, KU Leuven from the design tools perspective, and then Brightlands Materials Center, who's predominantly looking at integrating in moldable plastics of flexible electronics. DSP Valley is the organization that I work for. I am the CEO of DSP Valley. My name is Dieter Tersen. And we are the odd one out on this picture because we are not a research center. We are a cluster organization doing business development for the digital ecosystem in the region. I'll make very briefly use of the opportunity to explain what DSP Valley is doing, if I may. DSP Valley is breeding digital business. We bring together ideas and applications in order to distill viable concepts and bring these to fruition. We do this for the digital ecosystem, which by now is very deep and very broad, because digital electronics starts with materials, starts with design tools, and goes all the way up to big data, artificial intelligence, and online feedback systems that operate them. DSP Valley is active in 4 application areas. We look into smart health, smart industry, smart cities, smart mobility. And we do that for the benefit of the technology industry. So we work for this one big enabling technology field, digital technologies. And flexible electronics is definitely one element of that. DSP Valley works in the Benelux region. We have 3 offices, one in Eindhoven, one in Antwerp, and one in Leuven, where our headquarters are. This collaborative business development that we conduct is performed in a pretty standard funnel model. We start by informing as many companies in the network as possible. Then we connect them around some interesting, hot new topics. We cultivate viable ideas. And once we have achieved results, we consolidate the outcomes into regional assets. A number of companies in the network choose to help us do that and help carry the heavy weight of this collaborative business development initiative. Now, back to the project. And mapped out on the same process flow that I used to describe DSP value, you see that we are working in this project on the blue circles, which is the bottom side of the realization. We are addressing the entire physical realization part of novel formable electronics and how to put them into devices. And we do that, as I explained already, by installing infrastructure and by ramping up design tools to do so. Flexlines is not standing on its own. Within DSP Valley, we try to bring flexible electronics as far as possible, and we have additional projects to help innovative companies out with some of their problems, issues, and challenges. Whereas Flexlines is installing infrastructure and design tools, we also have a European project called Smarties. And within Smarties, almost 50 application experiments will receive funding to implement new flexible electronics ideas. And we take it one step further even with the SmartTex project, yet another European project where the integration of flexible electronics into textiles is being trialed. And again, there we have money available in the consortium for application experiments for innovative companies. Incidentally, for Smarties, you see a link on this slide where an open call, which is going to close in 10 days from now, is still active. And if you have any good ideas or interested in collaboration, please visit that website and submit your idea. Not only on technology, as I explained, DSP Valley also works on applications. One of the prime applications that comes to mind for flexible electronics is health. And there we are working together with Flanders Bio and Medtech Flanders in an initiative called Flanders Health. Again, an interesting initiative to connect to if you have applications in the medical field, in the healthcare field, and definitely if there's a flexible electronics aspect to it, there's many ways in which we can help you with that. Enough said about that. I hope this was clear from a perspective of introducing the project and a brief introduction to DSP Valley. I happily give the floor now to Romano from IMEC, who will explain to you the one-stop shop concept that we are implementing. Romano.
Yeah, thanks, Dieter, for the introduction. So my name is Romano Hofman. I'm Program Director at IMEC and also General Manager of Europractice. First of all, I would like to apologize for my appearance. You can see my hair is quite long, and I only had an appointment for Saturday, coming Saturday, so this webinar came a bit too early for that. So in today's presentation, I will present actually the one-stop shop we are working on in Flexlines. It is the gateway for customers to contact us and also to use the technologies. So as the subtitle says here, is the easy access to fabrication of flexible electronic prototypes. Yeah, okay, I'm trying to change the slide. So the main objective of the development of the one-stop shop is to create a one-stop service where both academia and companies can realize their ideas and have their ideas really fabricated in flexible and cheap electronic applications. So in order to do this, we have to do the following. So we have to mature the technology, and we also have to make a compliant design process flow, and that we develop also inside the Flexlines project. And we reach out to customers for developing and really stimulating them to come with ideas that can be realized in these technologies. So I don't do this alone at IMEC. My colleague Riet Labie is actually the main person driving this. And then, of course, we also rely on our partner TNO, where the fabrication is happening, and DSP Valley for the everything that is related to communication and outreach. So first, we want to identify what, how, who. So what do we offer, and what are we gonna offer? How will we offer it, and who is the customer? These are the essential questions we have to ask ourselves at the start of the project, but also during the project. Of course, we might steer into the right direction that these answers are receiving the right. These questions receive the right answer. So what? So we're gonna offer thin film transistor technology or large area electronic technology, as you can see here in the picture displayed. So all technology is based on a polyimide film on which actually the transistor technology will be deposited. Like I said, this will be done in the TNO in the whole center clean room, and the design process will be supported from the IMEC side. So that is what we are offering within the Flexlines one-stop shop. Then how? So like I said, I'm the general manager of Europractice. So Europractice is a concept that exists already for more than 25 years. And we use in this service MPW prototyping. MPW stands for, as you will see also in later slides, for multi-project wafer. And we think that we can copy this process also for thin film electronics. So meaning that you share the cost, but also share the area with different customers, and therefore lower the barrier even further. So, like I said, the Europractice concept has been launched many years ago. So to be exact, in 1995, it has been launched by the European Commission to enhance European competitiveness in the global market, and to stimulate collaboration of several European research centers. And so by offering industrial ready technologies, and that's very important. So we offer within Europractice only technologies that are really mature enough to for customers to realize their ideas in. And that's why within Flexlines, where we bring the technology and the design kits to a certain level, that after the project, customers can really realize their first prototype in these technologies. So within Europractice, that was a bit too quick. Yeah. So within Europractice, we do that typically for silicon technologies, so ASICs, MEMS, and photonics. We also offer packaging, and like I said, we also want to complement that now to flexible electronics. So we're gonna use the multi-project wafer approach to lower the prototyping cost. The access to design tool software is also essential, and the customers will need that, so they are also available through Europractice. So MPW service for flexible electronics is in principle exactly the same as for silicon. The only thing is that the plate or the area that is used for prototyping is much bigger than a silicon wafer. So typically you have a plate of several centimeters, tens of centimeters by tens of centimeters, which is much bigger than a typical wafer. By the way, here on this side, there is a few wafers behind me, so you can see the typical size of a silicon wafer. And you can see here in the picture, that we share the cost, for instance, here with about 8 to 9 customers. Next slide, please. Yeah. So who? In the pilot phase, we are only inviting experienced designers from academic institutions, and those designers have been contacted already. And so they have received the design kit and all the information that they need to make the first prototypes. But after the project, we want to reach out also to companies and other academic institutions who are maybe not so familiar with the underlying technologies, but they still want to try whether our technology that we offer here can really be suitable to realize their business idea into reality. So therefore, I also put at the bottom of the slide here a note, and so that this last thing we only do after the project. So to make it very clear and to summarize it again, in the project itself, we have only invited experienced designers who are doing already a lot in these kind of technologies, and afterwards we will roll it out, and then also the one-stop shop will be really open for people and well, more people. Next slide, please. So the typical ecosystem, how we do that, is that the one-stop shop is in the middle. So at the bottom, you see the different customers. So on the left-hand side, you see an academic customer, and on the right-hand side, you see the industrial customer. Then on the top, you see 3 bullets. So you see CAD tools or design tools that are needed to make the design in this technology. You also see IP. So these are really already predefined IP blocks that can be used by customers. And then we have also the fabrication. And so like I said, the fabrication will be done in TNO, and the IP part will be mainly steered by IMEC. So IMEC will serve also as a design house. That is the gray one on the extreme right. So if a customer is not able to do the design himself, then he can always reach out to IMEC or to the one-stop shop of Flexlines, and then we can help you with that. So that is the typical ecosystem and the model we will use also for the one-stop shop in Flexlines. So we really can do this because we leverage on pre-existing things that we have done within EuroPractice, but also within IMEC IC Link. And so like I explained in my previous slides, we do this already for many years for traditional silicon chips, and now we want to roll it out also for flexible electronics. So therefore we use also the good things and you could say the mature things for making sure that also the one-stop shop for flexible electronics is going to be a success. And so that's why IMEC and EuroPractice are leveraging this development. So we do this in the flow, and I hope it is clear and not too small. So also here you can see in the middle part the Flexline consortium. At the bottom you see again the customers, and on the top you see our supplier network. And so typically we do business development, so we reach out to our network or to people outside of the network, and we say we have those technologies available and we can mean something for you. So then as a result, a customer might come up with an idea and he launches a request. So then you contact the Flexlines one-stop shop and we will help you. And the first thing we do, we will come up with a supplier process flow. So it means we will help you with the needed IP, but also access to the design tools that you might have or might not have yet. And then, of course, we also enable you with the right design files you will need to design in the TNO technology. That is essential because otherwise it's impossible for you to make a design and to realize your idea in reality. So then you can see once you have the design tools and everything ready, you can start your design. So that happens again at the bottom. So then you have your design, and then you submit that design, or there is an iteration typically between us and you on the design, and that we call then the process of design checking or design verification. And once then the design is completely error-free, then we go into device and system fabrication. So it means that with your design we can realize it in our technology. And then in the end, we send the prototypes to you, which you can test and validate. But then it could also be, again, an iteration, because it might be that in your first design, there were still a few errors, or the technology didn't do exactly what you thought it would do. And then you can do a redesign. And so then you get a loop. But if you are happy, then typically, within EuroPractice, we can also facilitate upscaling, meaning that you can go for multiple prototypes. So typically, in our case, we will give you about 10 to 20. And of course, if you will have to prototype, then you have to contact TNO directly to really make sure that you get more volume. And then for academics, of course, there is also the route that once the prototype is really working, that you publish it so that you get a publication out of it. And so that are the two distinct different routes. So on one hand, you have for the academics, the publication, and you can see here the smiley guy with his hands in the air, who's very happy that he has a lot of profit because his business became a success thanks to the Flexlines one-stop shop. So that is actually, that summarizes a bit what we are doing at the moment. So by the end of this year, we are really ready to support you with our technology and to get your prototypes into reality. So having said that, I mean, I'm open to any questions you might have, but we can answer them after the talk or now. I mean, Dieter, what do you prefer?
I'm checking if there are any questions available yet in the chat. Yeah, I see from Peter Visser, how do we scale this industry after the project demo prototypes?
Yeah, well, that's a very good question. So I would say when it's low to medium volume, then probably it can still happen in TNO. Of course, if it goes to higher volume, then it's another question. So then we need to find a fab. Typically for silicon, that's in the Far East. For this technology, it's not necessarily in the Far East. It could also be in places, like the UK or others. But then the technology needs to be ported to that fab, and then the customer can go that. But at this moment in time, we don't foresee that yet, and because we are really in the prototyping phase, and then it also goes outside of Flexlines. So like I said, Flexlines is really prototyping. As soon as a customer goes to volume, then we will divert that customer to TNO, or we together with TNO will find a solution for that customer for increasing his volume.
Okay. Romano, there's another question that popped up. Do you use any inkjetting techniques to realize strain gogs made from silver nanoparticle inks, graphene inks, etc.?
Yeah, well, that's a question I'm going to pass to Auke, because Auke is going to explain a bit more about the technology itself. So like I said, I'm just explaining the one-stop shop. So all details on the technology and also on the design, that will be later covered by Mohit. So I think that I will pass that question.
Okay, perfect. Then the inkjetting question was the perfect hinge to move on to our next speaker, which is Auke Kronemeyer from TNO, talking about the infrastructure. Auke, the floor is yours.
Yes, so thank you all. Thank you all for joining also this webinar on Flexlines. My name is indeed Auke Kronemeyer, working at TNO/Holcenter in Eindhoven, Netherlands, and responsible within this project indeed for the realization infrastructure. So indeed the question here in the app is a really valid question, but let's first just discuss a little bit about what we like to put forward within this within Flexlines essentially, because connecting to the question, it needs to be a relatively mature level of technology to actually offer the prototyping. So that means we have a subset of what is Holcenter in itself, a larger institute working on flexible electronics. We have a subset of the capabilities that we actually really offer within Flexlines. And if I go to my next slide here, immediately the core of the technology that we are really sort of offering within Flexlines is oxide transistor array technology on foils. So it is about small display technology. So thinking about the display you're looking at the moment, it's a pixelated electronic device where every single pixel you can address in a simple fashion, essentially, and sequentially. this type of technology, we have now quite some years of experience to transfer that into foil, where actually you'll also see now, for example, products coming to the market as the Samsung Fold phone, or the Huawei Mate 10, or there is a Chinese company, Royole, who was the first to actually bring a foldable phone to the market. This is the core technology that we actually bring in. And if you then look at what is the technology platform, it is specifically amorphous IGO technology. I will talk about that later on. But already going from flexible displays, which has been the core driver for this technology, we also have diversified that into imagers. I always call it displays is current in, light out. Images is reverse it, light in, current out. And also we have diversified that into flexible circuitry. So sort of NFC tags, those kind of type of applications. And of course, there might be other, that's why I dotted here, other applications that people are been thinking about, which we haven't really considered at the moment, but might be such an entry to the one-stop shop that if you have this idea, is this possible in this technology, then there might be all kind of other application domains than the three that we actually have done here. So I will go through them a little bit more in detail, just also to show a little bit what the technology is capable of. So first of all, one slide, yeah. Thinking about what Romano has been introducing about the multi-project idea, let's call them multi-project plates maybe here. Europractice is about wafers. Here we talk about plates. You see here an image of such a plate with, I guess, my old iPhone next to it as a sizing reference. It is 32 by 35 centimeters that we are working on. And the idea is to be compatible with this complete display industry. The idea is to use all the processes and tools, etc., that the display industry is aware of making displays on glass, which is probably the one you're looking at the moment. But then before you start the process, you do something of a foil on this glass, and this is your new substrate. And then you run with this new substrate everything through your existing display line. And at the end of the line, at the end of the whole process, when the display is finalized, you actually take that full-fledged product, you take it off the glass carrier and you have it on foil. And there's an example that you see here on the picture where it's a yellowish polyimide foil because it can withstand a little bit higher temperatures. But after the full process, you take this foil off of the glass and you have your electronics on foil. So we have at Hall Center chosen for a specific semiconductor technology, which is called amorphous IGZO. It's an oxide type technology. There's other technologies that are similar in performance, such as low temperature polysilicon. We have also experienced how to, yes or no, transfer from a prototype working in amorphous IGZO technology into different display technology. But we have in our line amorphous IGZO. So here, this is an example of, not an example, this is an image of how our facilities actually look like. So these are clean room facilities, as you can imagine, because we are depositing layers of 200 nanometers and thinner, which is significantly thinner than your hair. So every dust particle which is actually on your plates can actually cause significant defects. Still, since we are a prototyping facility, as you see in the bottom right image, for example, our work is what I generally call semi-automated. That means a number of tools can handle automated plates, but also a significant portion of the work is still actually handwork from process engineers. That means also that we are perfectly positioned to do prototyping, but the bigger and bigger the volumes get, at a certain moment, it's not really cost effective anymore to do work at our site because since it is a lot of manpower work, there's no scaling down of the cost if you are going to make more and more of these, for example, displays. Now, anyway, what you see is in such a clean room, it's generally processes called PECVD, plasma enhanced chemical vapor deposition for dielectric materials. We sputter metal lines, etc., metal materials. And generally what it is that you do a lot of what's called photolithography, expose with light a material that is actually light sensitive, that you have actually coated on top of your deposited materials, and you etch back. And making a display backplane is etching this, or doing this process of photolithography and etching for like 6-7 times after each other. So what we also took up within Flexlines is also, like Romano was kind of sort of saying, okay, we can make multi-project wafers, and we also offer some kind of packaging. Here also we try to work along the same lines, that actually as an optional offer, we're thinking about integration technologies. So very often probably your display, as an example, your imager, your circuit will not be the final product, but it might be actually beneficial to integrate that, because also the flexible electronics, of course, has benefits in that it can shape into a certain a curvature, such as, for example, thinking about your car dashboard. There's an example here in the middle of the images, where you really think flexible electronics might have a benefit that it can be better integrated with existing nice curved surfaces. And that's why we are also engaging in the development of integration technologies of the electronics. And here comes back a little bit the question of, do we have actually what was a detailed question, the inkjetting. So we have inkjet techniques available. I would call it in this case specifically an optional offering. As I said at the beginning, it's not at the same level of maturity that if you want to do prototyping, immediately all the processes will work together. But we can, of course, discuss about prototypes with inkjet printing in there. So as I said, what we are doing is application prototyping, and we have applications in displays, image sensors, and TFT circuits, and that is where I just want to give you a couple of examples. And in that sense, I'd like to start with what is the cross-section of an AMOLED display, because from there on we can also easily go into imagers and circuits, where you here see that the core is still this making of a TFT backplane array, which is can people see my mouse? I don't think so. So up until more or less the green layer, up until there, slightly above halfway, that is the TFT backplane. So that is actually the electronics that actually makes it possible to address single pixels. And then from the interlayer onwards, you generally couple what is the TFT backplane with something which is called the front plane. And here the front plane is because you make a display. It is a material that will start to emit light when you put current on it. So, and that is an OLED material in this example. So just quickly run you through once more this process. Yeah, our idea, our vision, and this is how flexible phones are currently made, or the displays for flexible phones, is monolithic integration. Stack everything up from the bottom up, every layer after each other. Do this with a glass substrate with foil on it. And also, since you might know or not, if you make a display, at a certain moment also you need driver chips that need to be bonded on there. So you have gate and data drivers and flex bonds to actually connect everything to the outside world. Also, these chips and flex bonds, they are connected to the displays already, or still when everything is still on the glass carrier. And only when everything is really fully finalized, you do what is called the delamination. So you take the flexible product off the glass carrier. Now, here's an example of the type of TFT technology we employ. It's called dual gate self-aligned TFT. I don't think you should really consider here what is the performance, but just an example about what is it that you can offer. A TFT is actually a switch for electronic current, but dual gate means you kind of have two switches. So we offer this technology because it gives more versatility for the type of circuits you can design, because you suddenly have sort of two taps or two knobs on your tap to actually make current flow or not. And if you look at the right side, what is of course important from a prototyping or from a facility that can actually do this at a relatively high maturity level from the technology point of view, is that at all the TFTs you make, and this is just a measurement curve that you see here, it's called the transfer curve of a TFT. But of course, this curve, this performance of TFT should be the same if you measure a TFT to the top left of the plate, for example, and the bottom right of the plate. And what you see here is actually an image of 75 measurements distributed all over this plate of a TFT of a dimension of 3 micron, where the performance you see is nicely uniform over the full plate. Now, then on top of that TFT array, you have to make your actually, in this case, AMOLED pixels. So you have all kinds of small contacts with under every contact is sort of pixel circuit that can drive it. Then you put the OLED there on top, and you start actually bonding the drivers and the FPC. And then at a certain moment, you have here a delaminated flexible display. So I have normally some videos actually from a couple of prototype examples that we have in here, that we have done here, but we cannot show video here. So these are stills from the image, but the idea is here to show that we have now quite some extensive experience in making for various display partners prototypes of flexible displays, where actually, of course, the knowledge and the know-how is in how you actually make the technology, but also the offer that we have towards these people is how can you also maybe change pixel circuits? How can you change driving schemes so that you can, for example, lower the power consumption of displays, or, for example, increase the uniformity of the light output? Those kind of things you should be thinking about. Now then, getting back to kind of that image of what is the cross-section of an AMOLED display, you can now take what is called this front plane away, and instead of putting now a OLED front plane, you are actually connecting your TFT backplane with what we call organic photodiode front plane. And then connecting that up with a material that can actually convert X-rays into visible light. And the visible light we measure with the image array detector. We can make flexible X-ray detectors. So this is an example for the medical industry, where actually if you go for your CT scan or your X-ray scan in the hospital, it's very often a very large and bulky system. That is what you might be able to reduce by actually used curved detectors. And also, generally now there is a trend, of course, that the X-ray detector comes to the bedside of the patient. But then this is still a very, very sensitive detector because it's very brittle. It's made of silicon. If you drop it, it is so many tens of thousands of euros gone. And with flexible technology, we believe we have an advantage there since it is less prone to breakage. The same technology, if you now take away this conversion of X-rays into light photons, you can use for actually large area fingerprint scanner. So this is an optical fingerprint scanner. So essentially there's light somewhere scattering around. It's very sensitive, so it doesn't need actually really a backlight. There's light scattering around. And depending on if it scatters a lot from your finger, from the ridges or valleys of your fingerprint, you can measure that at high resolution and determine the fingerprint. Also here, this was supposed to be a movie, but here I tried to show that actually our detectors are so sensitive that the heartbeat, if you put your fingers on the detector, our fingers expand and disexpand. It's probably not a good word, but I don't know what is the English word, but they get bigger and smaller when there is a pulse of blood coming through your fingers. We can detect that in real time, these changes in the optical reflectivity of your finger, and also extract, instead of only your fingerprint, we can also extract your heartbeat. So this is a anti-spoofing, standard anti-spoofing way to show that people are actually trying to get access to your building with a live finger instead of a dead finger. So if you think about also, for example, let's take the example of mobile phones once more. There you see that the trend has been to make the display even bigger and remove all the buttons. And there's also the fingerprint unlocking of your phone going on. And there is ideas and wishes to actually make your full display of your mobile phone fingerprint active. And there is multiple things, technology solutions, how you might be able to solve that. But one of the possibilities is, for example, make a very, very transparent fingerprint scanner and laminate that on top of your existing display. And here we made actually a prototype with the imager technology, where you see the person on the image puts its finger there on something which looks like glass, which looks like completely transparent. That is actually the active area for where you can actually measure the fingerprint. And we got a nice Flexlines result there to actually have a prototype award in one of the big conferences for the display industry called Display Week. The next step that you can do with images as well is now move into sort of the different light energy domain. So here, for example, instead of going for fingerprint, which is done with green light more or less, which is not going to protrude so much into your fingers, which is of course needed because you want to look at the surface of your fingers. If you move to more infrared light, and here we make near infrared photo detectors and we combine them with our TFT backplane, you can start to look further and further into your body, essentially into your skin, and you can actually start using your the patterns of your vein for biometric recognition. So these are an example of veins that are being measured in the wrist of a person. And so this gives sort of an additional feature for biometrics, which is, of course, combined with fingerprint, more of a security feature. Now then, as a third example, what we can do is also leave out completely this front plane. So don't do anything with light absorption, don't do anything with light emission, and then you can make circuitry. Here we have actually some examples where we actually make what we call capacitive touchscreen tags. So if you know something about an NFC tag that generally needs an antenna where you actually need to communicate with, here the idea is to actually use tags that are communicating capacitively with a touchscreen. And we have some nice exposure on that. And then I'd like to talk about this integration technology, some examples that we did there. So here, for example, I name a number of them where we have some experience with. We can do something with the lamination, inlay lamination. There's things about injection molding and thermoforming with plastics. And we are also thinking about, as also Dieter at the beginning explained, textile integration. So here's, for example, taking one of these chips that I quickly moved over. If you take these chips that are made on a plate, you first have to just get them into a roll format. This is the normal format how you would get functional tags. So you have this plate to tag process that we have lined up for this. And then if you just laminate such a chip with an antenna and this antenna chip combination, you can do it in paper again. You, for example, can make, let's call it functional playing cards. So cards that are active, that have a nice additional electronic feature in there, which can be, again, anti-spoofing, or it can also have a functionality in the game. For injection molding as integration technology, here what I'd like to show is just an example where we made a sort of functional demonstrator where there is RFID and NFC capability made on foil. We have actually put LEDs onto the foil, and then this whole sort of electronic feature is being put in rigid plastic by injection molding. And in the image, you see that if the phone gives enough power via the wireless connection to the sort of prototype devices, you can show that you can light on the LEDs in the plastic. So here you have really shown that you can integrate flexible electronics really within the plastic by injection molding. And the final example, what I'd like to show here is alluding to this fact that you can actually shape flexible electronics into a 3D format, or this is a 2D format, but okay, it's a first prototype. These are generally test samples, small arrays of the fingerprint scanner, for example, organic photo detector arrays. And we have actually, with a process, taking them off the glass, putting them into a thermoformable plastic, shaping it into the shape that you want it, and still showing readout, is that you can make really curved detectors. And we are aiming for a curved fingerprint detector, which has increased resolution compared to, if you look at the readout to the right, where the 16 by 16 sheep that we have imaged as a test here. But it shows the compatibility of our technology, of all the electronics and the photodetector front plane, with all the integration processes performed for integration into plastic. As a next step, also, if you talk about, for example, this previous example being a 2D shaped object, you can also, of course, start thinking about 3D conformable electronics or even stretchable electronics. And here we have actually engaged into a pathway where you start connecting, let's call it rigid islands, with flexible meanders, so flexible spring-like metallic structures. And in this way, we have actually been making stretchable displays. This should have been a movie as well, but I hope this image, and we have used this image for Flexlines as well, gives you a clear flavor that with these spring-like structures between the light-emitting islands, you can really make this into a conformable display. And also, since it is so conformable, you can also start integrating it into textile. So you need a couple of other processes to laminate it now into the textile material. But the example images to the right with the green heart and also the TNO logo in blue on the doll, or whatever you call it, shows that you can really integrate functional displays into textiles. And normally I end with this nice sort of kimono movie. I try to make a still out of it here, but with a Asian display partner, we transferred this technology actually. So addressing the upscaling question also before a little bit, this is technology that was actually prototyped here in Eindhoven at Hol Center, and after that transferred to the display partner, where they were actually demonstrating these into these nice kimonos. So that's where I would like to stop for today from the technology side. So I hope I've given you a flavor of what is possible, what we can do with the technology, and what type of technologies we are employing. And I can probably start answering some questions. I will do that later. But if you have now the technology, Mohit will in a moment present how you would come from an idea to actually designing into this technology before we are going to make it.
Perhaps, thank you, Auke. This was a very impressive rundown. Perhaps there's two questions from the audience we could take at this point in time. One is about the thermoforming that you mentioned. When thermoforming, the conductive material needs to be stretchable. Do you have stretchable materials, or do you compensate for stretch through something like meander structures or?
Yeah, we do. So we do both actually, and it's a very good question. It depends a little bit on, of course, on the application. That is a no-brainer, but it depends on the resolution that you need. So if you want to have a very high resolution pixelated array, for example, for your application, you don't have the space for meanders, because meanders take space. And therefore, you need to work with other solutions to actually take this into account. Actually, for example, for the example of the OPD thermoformed imager, there is no real specific thing that we did with materials that are intrinsically stretchable, etc. It's just because you make electronics on foil very thin that you can afford this bending radius. At a certain moment, of course, the bending radius is not is not feasible. A small bending radii are not feasible anymore. But to a very, very large extent, you can still do this with thin down, very thin on foil electronics.
Okay. And then there's another very interesting question as well, I find, but perhaps not one that we can answer in the confines of this webinar, but it's about a project that has been initiated, Engineers Pro Physicians.
Yeah.
And it's related to this COVID crisis. We're actually integrating electronics into mouth masks, into PPE, with bactericidal and antiviral properties could actually be a darn good idea to work out. Now, again, I don't think we can answer that at this point in time, but I would like to suggest the person that submitted the question to contact us. We have a flexlines.be and a flexlines.nl webpage. Please contact us. Because I see something in synergy with, for instance, the Smarties project that I mentioned, where actually subsidy money is available. Within Smarties, we have decided to dedicate projects in the June call to COVID combat, and this might fall into the category. So I would personally also be very excited to continue the discussion on that one.
Yeah, and just technologically, just to give a short answer, we do also some surface mounting of components. So here it says sensors. We also do LEDs. We do RFID chips, etc. All kinds of tin down silicon chips. So we have some experience with pick and placing, etc. of components. So I think there is definitely scope to actually discuss this a little bit more in detail. I would be very happy to do that.
And then there's a last question coming in. What will be the next step to discuss elements further, especially with respect to this integration, injection molding and stuff? I'd say please contact us on the website. The contact details from Auke and from some of the other presenters are just right there available.
Yeah.
And then we can quickly contact you and see how we can best support or how we can best collaborate. I think in view of the time now, it's probably best to pass the floor to Mohit Dandrekar from the KU Leuven, who will enlighten us about another very interesting topic with respect to flexible electronics, and that is how the hell do you design them in a proper way. So Mohit, it's all yours. Please take it away.
Hi, thank you. My name is Mohit Dandekar. I'm a researcher at KU Leuven, MICAS Labs. I've been working on the circuits and systems aspect of the design in IXO-TFT technology. So as you can see in the image, that's basically the idea to make fully integrated electronic systems on foil. So just to give you an idea, what Auke has already covered actually, where flexible electronics could go. So for example, on the top left, you see that they can be integrated in paper cards or in labels for products or indeed in form of biomedical applications, which could go directly on the body. One of the examples which was presented earlier was also a large area imager. These are typically applications which naturally require larger areas. It's difficult to integrate at that larger scale in silicon monolithically. So this type of technology indeed does present an advantage. So to give you a comparison between like a CMOS chip versus a flexible chip on foil, CMOS chip is made on silicon wafer, which is very brittle. You can't bend it. It's also restricted to smaller sizes, as you can see on the left. While the IXO-TFT thin film is integrated directly on plastic foil, and you can go up to comparatively fairly large areas. Of course, the performance is not as good as conventional silicon, but the cost per area benefit is quite apparent. So to do a slightly more detailed comparison, so the IXO-TFTs that we use sort of fall in the middle. On one extreme, you have printed electronics, as one of the questions asked. Those electronics use some conductive inks, etc., but they're not easy to scale. They're not very precise either. Of course, the gold standard is conventional silicon processing, which is very precise. You can scale it down to nanometer sizes, but it's also quite costly. So just to give an idea of how large a large area could be, so amorphous silicon, which has been used conventionally in the display technology, can scale all the way up to, as you see in the right side of the image, that's to scale. So several meters by several meters. A more detailed overview of the comparison of different technologies is in this slide. So what we use, as Auke said, is the amorphous indium gallium zinc oxide, IGZO, semiconducting material. It On most of the grounds, it falls quite in the middle. On one side, you have amorphous silicon, which is extremely low mobility, as you see in the top row. On the right side, you have silicon, very high mobility. Amorphous silicon is a fairly mature technology, but you can't get very fast circuits out of it. EXO offers a compromise in the middle. You also have some thin film technologies in silicon. They're called LPTS, low temperature polysilicon. But they have some disadvantages as compared to EXO, as you see. One of the things which makes EXO unique is that you can only make one type of transistor. In silicon, you can make two type of transistors, a P-type and an N-type. That's why it's called complementary MOS. But in EXO, it's only one type of transistor that we can make because of the underlying physics of the material. As far as the manufacturing goes, Auka has already covered it in quite detail, but I'd just like to capture one point is that you don't need as many mask steps, number of process steps to make EXO circuits as compared to silicon. So to talk about the device itself, basically it's made on a carrier, glass carrier on the bottom, on which we put out the plastic foil on which the circuits are finally going to be. There is a barrier layer followed by the semiconductor and metallization on top. It's a very silicon-like processing. So looking at the device, the TFT, so this is on the right side, you see performance of several TFTs which have been taken on the paper, on one wafer. You see that there is quite a variation in the current that you get from different devices on the same wafer as well as on different wafers, and that's a problem for designers because they need to be able to predict how devices are going to do. So the variability has to be taken into account. Also, there are limited metal layers, which makes it an issue for automated routing of and interconnecting all the devices to form circuits. One of the issue also is that because this is a newer material and newer device, models are not readily available. So our team has developed some models for helping the designers to design their circuits. As you see here, this was published in Date last year. The symbols are the measurements, and the solid lines in red are the device model that we use for our circuit simulations. So of course, we also take into account that we have dual gate TFTs, and we have device models which work for both independently driving both the gates. So coming back to the design challenge, which is basically the focus of the research work I do, is that in conventional CMOS, you typically have two type of devices. And if you take an example of a digital block, logic circuits, then you use one type of devices at the bottom, which is called the pull-down networks, the complementary devices in the pull-up networks. We don't have complementary devices. So it makes it difficult to make good pull-up networks. And so we have to use some interesting ideas to make digital circuits. The same problem presents in analog. That's an example of a very simple amplifier. You use a N-type device at the bottom to actually give the gain, and then you need to design a load with only N-type devices, which is hard to do. So this is an example of how you could start solving those problems. So this is a inverter, a very simple inverter made with only N-type device, the EXO-TFT. And on the right, and in the middle, you see the response of the inverter as measured in the lab. If you can make an inverter, then you can make more complicated gates, and then you can put them together to make digital systems. Similar approaches have been taken for designing of analog circuits. So, of course, when you do electronic design, you need to use CAD tools. There are lots of tools available, and what we have done is put together a custom design flow using the standard industry tools, so that we can work at multiple levels of abstraction, from transistor level design to RTL design for digital, and then put them together to form fully integrated systems. To capture the kind of circuits that we have made in the kind of applications is we have made wireless tags, memories, microprocessors, displays. Some of them Auka already showed you. And so on the research side, what we do, we have validated various type of designs, ADCs, mixed signal circuits. In this slide, you see some pictures of the designs that have been made and published. The older ones are with organic TFTs. The newer ones are with the latest IXO TFTs. So some more examples of memories, non-volatile ROM memories. And to summarize, basically we are making wireless stacks, memories, and sensor interface circuits. So to summarize, basically we work in large area electronics from which we could make circuits for IoT wearables. IXO TFT tech that we use has silicon-like processing, so existing lines can be used or adapted to make these circuits, as Auka explained. They are faster than conventional amorphous silicon, cost-effective, and several proof of concept designs have already been made by my group, and I'm also investigating right now. One of the challenges is, of course, we have to innovate on circuit design techniques, given that we don't have complementary devices and the standard ways of doing electronic design, as in CMOS, cannot be directly applied. And we are also working on improving the device model so that we can better predict the circuits that we make before we manufacture them. So thank you. I'll just pass it back to Dieter.
Thank you very much, Mohit. Let me check if there are any questions coming out of the audience at this point. That does not seem to be the case at this moment. Then I think we can conclude, wrap up this seminar. I'd like to thank everybody for their attendance and for the interesting questions that we have received. And for those of you that would like to continue the discussion, which we very much would welcome, please have a look at the website flexlines.be or flexlines.nl and take contact with us on the topic that you would like to pursue. Thank you very much, all. We're going to close the webinar here and see you on a next, hopefully live event on flexible electronics.